So, question number 121. Look at the truss shown in the figure 12.40, and we have to draw the influence line diagram for force in member XY. Look, the total length of the truss is 6L, and we have to determine the influence line diagram for the force in the member XY, which is the vertical member of the truss. Okay, now for this member, the influence line diagram will be triangular in shape, and at this point X, the ordinate of the triangle will be B by L. B means 1 2 3 4 5 5L divided by full length of the truss, which is 6L, and then it will become 5 by 6. Option B is right answer. Question number 122. A truss is shown in the figure 12.42. The cross-sectional area of each member is A, capital A, and the modulus of elasticity of the material is capital E. The strain energy in the member XY is given by, look, these two member XY and this horizontal member, two non-collinear member and connected to a unloaded joint. Okay, this is the joint, but this is unloaded, so the force in both the member XY and this horizontal member will be 0. Okay, so as the force in the member XY is equal to 0, so the strain energy in the member XY is also 0. Option D is right answer. Question number 123. A rigid cantilever frame ABC shown in the figure 12.43 is fixed at C. It carries a load P at A as shown in the figure. Neglecting axial deformation, the vertical deflection of the point A is given by, suppose AB is the cantilever end. Let's assume the only AB part, which is the cantilever part of the frame. Okay, so the deflection under the point load P at the end A will be del 1 equal to PL cube by 3EI, as you know from beam deflection formula. Now at this point B there will be some moment, and the moment value will be equal to P into L. So M equal to P into L, and for this moment there will be rotation at the point B, because this is pin end, this is hinge connection, there will be no movement at C, but there will be rotation at the point B, and the rotation at point B will be equal to mh by EI, and m is equal to P into L, and h is this vertical distance, and EI is the flexural rigidity, which is constant throughout the frame. And for this rotation at the point B there will be additional deflection at the point A, and this deflection will be equal to the rotation at end B into this length L. So del 2 will be equal to mh by EI into L, and the calculated value will be PL square h by EI. Now the deflection at point A will be del 1 plus del 2, and if we add these two value, we will get the deflection value is equal to PL square by 3EI into 3H plus L. Option C is right answer. 124. The horizontal thrust due to a question number 124. The horizontal thrust due to rise in temperature in a semicircular 2-hinge arch of radius r is proportional to, we know the formula for horizontal thrust. H for a 2-hinge semicircular arch is equal to 4EI alpha into T divided by pi r square. Alpha is the linear expansion coefficient, T is the change in temperature, and capital R is the radius of the arch, and I is the moment of inertia at the crown of the arch. So from this formula we can easily say the horizontal thrust H is inversely proportional to the radius of the arch. Option D is right answer. Question number 125. For the continuous beam where flexural rigidity EI is constant loaded as shown in the figure 12.44, the moment at B is, so A, B, C, this is our continuous beam subjected to point load at this span AB, at mid span of AB, and also a point load to the mid span of BC, and total length of the continuous beam is 2L. Okay, so this continuous beam is divided into two parts, AB and BC. Length of AB is equal to L, and length of BC is also is equal to L. So free end moment at the midpoint of the span AB and BC will be WL by 4. This ordinate and this ordinate will be WL by 4. Now we have to determine the moment at B. This is fixed end moment. Okay, now to determine the moment at B, we will use three moment equation, which is 2mb into L1 plus L2 equal to 6a1 x1 bar by L1 plus 6a2 x2 bar by L2. mb is the moment at B, L1 is the length of the span AB, L2 is the length of the span BC of the continuous beam, and A1 is the area of this bending moment diagram of this span AB, and A2 is the bending moment diagram of the span BC. X1 bar is the distance of CD of the triangle formed by the span AB from the support A, and x2 bar is the distance between the center of gravity from this triangle to the end C, and we know L1 and L2 value. Now if we, so the value x1 bar will be equal to L by 2, and x2 bar will also be equal to L by 2, and A1, which is the area of the bending moment diagram of the span AB, which is equal to, and A2 both will be equal, and area of the bending moment diagram formed at this span AB and BC will be equal to half into base length is L, and ordinate value is WL by 4. So A1 A2 will be equal to WL square by 8, and L1 L2 will also be equal to L. Now putting all the value in the equation number 1, that is 3 moment equation, we will get the value of MB is equal to 3WL by 16. Now if we make the ratio for moment at B divided by free moment at mid span, then the ratio will be 0.75. So moment at B will be equal to 0.75 into free moment at mid span, where the span is AB or BC. Okay, option A is right answer. Question number 126. A fixed beam AB of length L having constant flexural rigidity EI carries two loads P at its third point C and D as shown in the figure 12.45. Numerically, the maximum bending moment will occur. So this is our fixed beam AB subjected to two number of point load. One point load is acting at a distance L by 3 from A, and the another point load P acting at a distance L by 3 from the support B. Now reaction at A is RA and reaction at B is equal to RB. Then RA plus RB will be equal to 2P. Now if we take moment at point A, so summation of all the moments about the points A is equal to 0, then all the moment value will be minus RB into L in anti-clockwise direction plus this load into this distance 12 by 3, that is in clockwise direction, plus this load into this distance L by 3, this is also in clockwise direction, is equal to 0. So after calculation RB will be equal to P, and as we know RA plus RB equal to 2P, so the value of RA will be also P. Now let's see for a fixed beam AB when it is subjected to a point load that is at a distance A from the fixed end A and at a distance small b from the support B, where total length of the beam is L. The fixed end moment at A is equal to PA B square by L square. So for this beam AB, the fixed end moment at A will be, let's assume this load is absent. So under this load, the fixed end moment at A will be P into this length A into this length 12 by 3 square by total length L square, plus let's assume this load is absent. Now plus moment at this point, which is equal to load into this distance 12/3 into this distance L/3 square by L square, total length of the beam. And after calculation, the value of fixed moment at A will be MA is equal to 2PL by 9. Option C is right answer. Question number 127. Consider the following statements. Sinking of an intermediate support of a continuous beam reduces the negative moment at the support and increases the positive moment at the center of the span. Option A is right answer. Number 128. A number of wheel loads 3 ton, 4 ton, 5 ton and 6 ton spaced 2 meter, 3 meter and 4 meter respectively move on a simply supported beam AB of span 24 meter with the 3 ton load leading from left to right. To find the maximum bending moment at 18 meter from A, the load that must be placed at the section is. So this is our simply supported beam AB of length 24 meter, and we have to determine the maximum bending moment at a point C, which is at a distance 80 meter from A, and these beams subjected to a series of wheel loads 3 ton, 4 ton, 5 ton and 6 ton. These 3 ton and 4 ton are spaced at 2 meter, 4 ton and 5 ton spaced at 3 meter and 5 ton and 6 ton spaced at 4 meter. We have to determine under which of these wheel loads we will get maximum bending moment at point C. So with respect to point C, we have to satisfy an equation, and the equation is AC by BC. That means the ratio of length AC by BC should be equal to the ratio of the load. One, the loads on the left side of the point C, the ratio between the load on left side of the point C and the load on the right side of the point C. So on the left side of point C, the loads are 6 ton and 5 ton, that means 11 ton, and on the right side of the point C, only the load is 3 ton. Okay, if we calculate by placing the 4 ton wheel loads at the point C, this equation is nearly satisfied. Otherwise, this equation is not satisfied at all under any wheel loads. So the ratio of length AC by BC will be 18 by 6, and the loads on the left side of C will be 11 ton, 6 plus 5 ton, 11 ton, and loads on the right side of point C will be only 3 ton. So the ratio will be almost same. This is 3 by 1 and this will be 3.66 by 1. So nearly satisfied to get the maximum bending moment at point C when 4 ton load is placed at point C.
Option B is right answer.
Question number 129. A load W is moving from left to right support on a simply supported beam of span L. The maximum bending moment at 0.4 L from the left support is. So this is our simply supported beam AB, and a moving load W is acting at a point 0.4 L from the point A, and total length of the beam is L. Okay, now we have to determine the maximum bending moment at point C. At point C, the maximum bending moment will be W into A into B by L. A is equal to 0.4 L and B is equal to 0.6 L. The bending moment diagram will be triangular in shape. The maximum bending moment ordinate will be WAB by L at point C. And if we calculate, the maximum bending moment value will be 0.24 WL. Option C is right answer. Question number 130. Consider the following statements regarding the beams and their loading shown in the figure 12.46 and 12.47. Deflection at B of the beam in figure 12.46 would equal. So here in figure 12.46, the beam cantilever subjected to a uniformly distributed load of length L is a real beam, but the beam shown in the figure 12.47 is conjugate beam, and the deflection at any point in the real beam is equal to the bending moment at the same point into the conjugate beam. So statement 1 is correct, that is given figure 12.47, and statement 2, that is 1 by EI into moment of area about B of the bending moment diagram of the beam in the figure 12.46, that is also right, because if we want to find out the deflection at point B of the cantilever beam shown in the figure 12.46, then by moment area method we know the formula will be equal to the area of the bending moment diagram and the center of the bending moment diagram from the point B into 1 by EI. For this cantilever beam subjected to uniformly distributed W per meter of length L, the bending moment diagram will be like this parabolic. Maximum bending moment at the fixed end W square by 2, and the CG of the bending moment diagram is 3/4 L from the point B. Now deflection formula will be 1/3 into base is L into height WL square by 2 into the CG distance from B is 3/4 into L into 1 by EI. That means and the deflection will be WL to the power 4 by 8 EI. Option B is right answer. Question number 131. Which of the following pairs of a given beam and its conjugate beam are correctly matched in the figure 12.48? Look, in real beam, the outer simply supported end will remain same simply supported end in conjugate beam. But in real beam, the free end becomes fixed end in conjugate beam and fixed end becomes free end in conjugate beam. And the internal simply supported end becomes internal hinge in conjugate beam. So as per this discussion, statement 1, 3 and 4, they are correct. Option B is right answer. Question number 132. A cantilever beam AB fixed at A and carrying a load W at the free end B is found to deflect by del at the midpoint of AB. The deflection of B due to a load of W by 2 at the midpoint will be. So this is our cantilever beam AB subjected to a point load W at the free end, and by this point load deflection at the midspan is del. Okay, now if the load W by 2 is subjected at the midspan of the same cantilever beam, then what will be the deflection at the point B? So by Maxwell's reciprocal theorem we can write this load into this deflection equal to this load into this deflection. So by doing that, the deflection del B at here will be equal to del by 2.
Option C is right answer.
Question number 133. The frame shown in the figure 12.49 is subjected to loads as indicated. The intensity of lateral load is 2 kN per meter. The shape of the bending moment diagram for the frame will be. So this is our portal frame subjected to a vertical point load at the midspan of the frame and subjected to uniformly distributed load at this vertical member right side of the frame. Okay, that is 2 kN per meter. Suppose this vertical member length is 4 meter, which is not given in question. So let's say this is 4 meter and this is 2 meter given, and this member length is 4 meter. Now we have to determine the bending moment diagram for this frame. Okay, so in shortcut we just have to choose the right option of bending moment diagram for this portal frame between 4 diagram. Okay, so for the sake of simplicity we will just choose the right bending moment diagram for this portal frame. Okay, with respect to these loads. Now see, for this horizontal loading there will be horizontal thrust at this point and at this point, these two support at these two supports. Okay, so suppose there will be some horizontal reaction here at this support, and at this support there will be some horizontal reaction at this support. Okay, now say at this section some horizontal reaction is available, so at this point there will be some moment through this horizontal loading, so force into distance, then at this point there will be some moment that is negative. Okay, now this on this horizontal member, the due to the vertical concentrated load at the middle, the free moment value will be WL by 4, as you know, which is 10 into 4 divided by 4 equal to 10 kN per meter. But at this end there will be some fixed end moment. Okay, and that value will be equal to PL by 8. P means load 10 kN and L means 4 meter, and divided by 8 will be equal to 5 kN meter. Now at those two end, at these two end there the 5 kilonewton meter fixed end moment value will be available. As I said earlier, there will be some horizontal reaction at this end also. So at this point, due to the horizontal reaction, there will be some moment. So this moment will be negative. Now due to this load, this UDL load, there will be some free moment which will be at the middle, which will be maximum at the middle, and the value will be WL square by 8. And if we calculate, the value will be 4 kilonewton meter. That is positive because this is free moment diagram. And the other fixed end moment due to horizontal loading, horizontal reaction, are negative. And the superimposed or combined bending moment diagram is the actual bending moment diagram of the portal frame. Okay, so by this shortcut we can choose the right bending moment diagram for this frame, and option C is right answer for question number 134. In the frame shown in the figure 12.51, support force settled by del. The fixed end moment in the horizontal member of the frame will be, where other symbols have the usual meaning. The fixed end moment in the horizontal member of the frame will be 6 EI del by L square. So 6 EI del by L is equal to 4 meters. So L square means 16. So option B is right answer. Question number 135. A plane frame is loaded as shown in the figure 12.52. The rotation are indicated as theta B and theta C, and the sway is indicated by the symbol del. So for the given frame shown in the figure 12.52, which one of the following statement is correct? So this portal frame is symmetrical with respect to the vertical axis, and the load is also symmetrical with this frame.
There is no lateral force in the structure. So
There will be no sway in this portal frame because we know sway is the lateral movement, or lateral movement is also caused by the horizontal loading or any type of horizontal force. So there is no horizontal loading. Okay, so there will be no deflection. So del is absent, but at the end B and at end C, slope will be there. These two slope will be equal in magnitude but opposite in nature.
to maintain the equilibrium of the structure.
D is right answer. Theta B equal to minus theta C, and where del is absent. Question number 136. For the plane frame shown in the figure 12.53, static and kinematic degree of indeterminacy are respectively. So for this rigid jointed plane frame, the degree of static indeterminacy formula ds equal to 3m plus r minus 3j. M equal to number of member, that will be equal to 11. 1 2 3 4 5 6 7 8 9 10 11. And R is the real number of reaction components. So three supports, one is fixed support, another is hinge support, and another third is roller support. So for roller support, one reaction component, that is vertical reaction component, is available, and in hinge support two reaction components such as horizontal and vertical reaction components available. And from fixed support, three reaction and components, one horizontal reaction component, one vertical reaction component, and one moment is available. So total 3 plus 2 plus 1, 6 number of reaction components available. So R will be equal to 6. J equal to number of joints will be equal to 1 2 3 4 5 6 7 8 9 and 10. So number of joint J will be equal to 10. After putting all the value into the equation, ds will be equal to 9, and degree of kinematic indeterminacy formula dk will be equal to 3j minus r. So we got j equal to 10 and r equal to 6. So by putting value, dk will be equal to 24. Option C is right answer. Question number 137. A truss of panel dimension 3 meter into 4 meter is shown in the figure 12.54. The influence line diagram for the force in the member U2L3 is, suppose the unit load is rolling along the bottom beam or bottom chord of the truss from here L0 to L6. Now the force produced in U2 and L3 is 0 when the unit load is at support, either this ends or this ends. if the unit load is at the supports, the force produced in the inclined member U2L3 will be 0, but the force produced in the inclined member U2L3 will change its nature as the load passes from the joint L2 to L3. Okay, and since the structure will deflect or sag under the action of the load, the joint U2 will be in compression and joint L3 will be in tension.
And the ordinary value in compression and tension both will be cosec theta, and the cosec theta value will be equal to 5/4, that means 1.25.
Option A is right answer. Number 138. What is the horizontal deflection at free end C of the frame shown in the figure 12.56? So this is the frame ABC cantilever frame rigidly connected at A. EI is constant throughout the frame. Now we have to determine the horizontal deflection at point C, which is subjected to a bending moment M. Now to find out the horizontal deflection at point C, let's apply a horizontal load P at this point, that is fictitious load, whose value is equal to 0. Okay, now let's take a section x dash at a distance x from C in the member BC, and let's take a section y dash at a distance y from the B. We know the formula for deflection at a point is equal to deflection for a point C will be equal to integration m into del m by del p divided by ei into dx. So the horizontal deflection at C will be equal to, for the member BC, integration value 0 to L m into del m by del p into dx by ei here, plus for the member AB, integration value 0 to L into m plus pui into del within bracket m plus pui divided by del p into dy. At this section y dash, the moment value will be this bending moment m constant throughout the frame, plus the moment due to the fictitious load p into y at this point. So that's why m plus py is the total moment value in the at this section of the member AB. That is why it is written m plus py. Now if we calculate, this term will be 0, and if we integration this value and calculate, the final value of deflection at point C will be m L square by 2 EI.
Option A is right answer.
Question number 139. Which one of the following gives the distribution factors for the member AE and AC of the box section shown in the figure 12.57?
So this is the box section A, B, C, D, E. As this is a box section, so we will consider all the end is fixed. Okay, and the value of stiffness K is equal to 4 EI by L. That is the formula when the far end is fixed, and the stiffness value will be 3 EI by L when far end is hinged. But here all the end is fixed as it is a box section. Okay, so stiffness of the member AC will be 4 EI by L. So 4 into E into I value is 2 times of this member AC. So 2I by L is equal to 5 meter length of this member AC. So the stiffness value KAC will be equal to 1.6 EI. Now stiffness value of the member AE, that will also be equal to 4 EI by L. So 4 into E into I divided by the length of the member AE will be equal to 2.5. So after calculation, KAE will be equal to 1.6 EI. Now total stiffness at a joint AE plus AC. So total stiffness value will be equal to 1.6 EI plus 1.6 EI equal to 3.2 EI. Now we know the formula for distribution factor for a member will be the stiffness of the member divided by total stiffness of all the member connected through that point. Okay, so through the point A, the distribution factor for the member AC will be the stiffness of the member AC divided by total stiffness of the member AC plus AE, because at this joint AE and AC is connected. So if we calculate, DF AC will be, the distribution factor AC will be 1.6 EI divided by 3.2 EI, value will be 0.5. Similarly, distribution factor for the member AE will be stiffness value of the member AE divided by total stiffness value of the member AB plus AC, that is equal to 3.2 EI. Now if we put the value, we will get distribution factor for AE will also be equal to 0.5.
Option A is right answer. Number 140, for the fixed beam shown in the figure 12.58, the influence line diagram for the bending moment at the midspan of the beam is best represented as.
So in question number 140, a fixed beam is given, which is a indeterminate beam, and the influence line diagram for indeterminate beam will be non-linear. Okay, now at the midspan of the beam, if we release moment, then the influence line diagram of the beam will be like this, non-linear, and the value at the midspan will be 1/8.
The diagram given at option A